So, Turing here stands for Alan Turing. How many people have heard of him? Okay, yeah, quite a bit. And might say a little bit more about him during the quarter as we learn more about Turing machines and other things that Turing did. And this is actually, we're coming up to his 100th birthday, sometime in June. And, all right. So I'm going to introduce Turing machines first sort of intuitively with a couple of examples and a couple of pictures, and then we'll, as we've done in the past, look at formal definitions of what a Turing machine consists of and what a computation in a Turing machine is, and then we'll look at some more examples of programming Turing machines. So first of all, a Turing machine has a control, which is sort of like what we've been used to. It has states and transitions, etc. So this is almost like a DFA in there. But the main difference, it's a huge difference, is that there's a tape. And this tape, it has an end on the left side, but it's infinite on the right side. And it's the tape where initially the input is written. So A, B, C, D, whatever. That's the input. But the Turing machine can also write onto the tape. So it's a read-write tape. Read. And also write tape. And this is called the read head. So the Turing machine has a read head which is over some particular character on the input tape or on the tape, the read-write tape, and in a single move can read a symbol, can choose to write or not, and can move left or right. Okay? So Turing machine moves on the tape, but now it's bidirectional. When we were talking about finite state machines, you were only progressing through the string. You could never back up. And in finite state machines, other than PDAs, you couldn't write anything. Okay, but now we have the ability to write on this tape. And unlike a PDA, the writing is unrestricted. We don't have to just use a stack. Okay, so it's a lot more freedom, and we'll see that that freedom has a lot of consequence in terms of the kinds of languages that a Turing machine can recognize. Okay, but inside here it's sort of intuitive, although we'll have to really specify. I mean, it's intuitive in the sense that it's similar to what we've been playing with so far, but we still have to specify exactly what goes on in here. And then there are some other differences that first seem small, but anyway, we have to specify them. And one is that in a Turing machine, as soon as you get to an accept state, you accept. So you don't have to have exhausted the input. Okay? And this also reflects the fact that you can be writing things on the tape and so on. And so you want the ability to accept even if the tape still has things on it or you haven't processed everything to the end. Of course, for most languages that you want to, for many languages that you're interested in recognizing, you need to have seen all of the input. So that has to be built into the control for how the Turing machine actually works. But formally, you are allowed to accept or reject as soon as you get into, well, you do accept or reject as soon as you get into an accept state, you accept, and as soon as you get into a reject state, you reject. So there's one specified accept state and one specified reject state. Okay, so let me give you a little bit of example. So we'll look at a Turing machine. Even without having fully defined what a Turing machine is, I'm going to show you an example, and then we'll define it more precisely. this is a Turing machine for the language B equals W hash W, where W is a string. Now, these should be squigglies. It's a binary string. Okay? So W is a binary string, then we have a hash, and then we have another copy of it. All right? We know this isn't a regular language, right? Although it is a language that we could accept, we could recognize by a PDA. Everybody, I think, has seen that. So let's see what a Turing machine does on this. Okay. So it's going to make multiple passes over the input. So here we have written on the input, let's say that we have some input which is actually in the language. We have input which is not in the language, in which case the Turing machine should reject. Let's do an example first, or think about first what happens with input that actually is in the language. And by the way, after the input, you have a space, and we represent a space with that silly half-empty or fully empty cup, or whatever you want to call it. Anyway, that represents a space, and we have spaces all the way down, all the way out. Okay, so this is what the input tape initially looks like. The read head is initially at the left end, looking at the first character. And so what would you want to remember? We can move left and right, and we can mark, we can write onto the tape, replace symbols. And inside here we have something that's kind of like a finite state machine. It has very precise, it has states and transition rules. The transition rules say that when you're in a particular state and you're looking at a particular character on the tape, you can choose what state you next moved into. You can choose whether you're going to overwrite that symbol with something else or not, and whether you're going to move right or left. So these are the kinds of decisions that the Turing machine can make at every step. So anybody have any general idea of how a Turing machine should go about checking whether this string is in this language? See, now we're a lot closer to thinking like an algorithm or a program. Okay. Admittedly, this is a pretty constrained computer, but you can think sort of at a high level first, and then translate that into the states and the transition rules. Okay. Unlike, let's say, when we were thinking about finite state machines, it was hard to think algorithmically at the top level because what you had to ultimately translate that into was so low level. But here we can think of a kind of a high level idea. Anybody have a suggestion for a high level idea? Yeah.
Is there a way to know the length of the W?
We don't know the length of W, but we do know that there's a symbol that separates the two copies.
So you can find it out using the hash. So I guess you could read the first character in the first W, and then go until you find the hash, and then read the next character, or the character that right after the hash. Right?
Yeah.
And then you can, I don't know, you kind of have to keep track of how many you went, right? I don't think you could do that.
Well, okay, but at the high level, so you're still thinking a little too mechanistically. At the high level, you want to see the first character here, and then somehow remember it, run over till you see a hash, which you can do by these right transition rules. And the hash separates the two copies, or the two things you hope are copies, and then you check whether these two characters are equal. Okay, now we don't have, this is not a high-level language, so we don't have an equality test. Okay, so that all has to be encoded somehow in the finite state control. But if these two are the same, then we're going to mark this one off and mark that one off. We'll change them to symbols that are not in the read alphabet, in the input alphabet. And then we go back here till we hit that symbol that showed that something was marked off. we read what the next symbol is. We run back over here till we hit the last marked off symbol, and we read the next symbol and see whether that was equal. Okay? So hopefully everybody gets the high-level idea. You haven't seen quite yet how we're going to translate that into the actual Turing machine. So this is what this is the way it's put in the book. The high-level idea is zigzag across the tape. Well, zigzag means it's going to go forward and backwards and forwards and backwards repeatedly. That's zigzagging to corresponding positions in the two strings that are separated by the hash. Okay? And check if they're the same. Okay. Well, this one, by the way, you really want to think about that. You have in here a finite control. You don't have a language which can take two variables and see if they have equal value, something like that. We're not at the level of a programming language. So how is it that the Turing machine is going to be able to check if they're the same? Anybody have an idea? Well, one thing I didn't tell you is that the alphabet for the input tape, this is the input alphabet, well, actually here we know what it is, but anyway, the input alphabet is finite. And that's a crucial thing. Here it's just of size 2. Okay? So the input alphabet only has 2 different possible characters. So when we see a character over here, we can move into a state, a particular state, which is, by the virtue of what state it is, it's remembering, it's recording, it's reflecting the fact that what you saw here was a 0, or in a different state, reflecting the fact that what you saw here is a 1. Okay? And then when you go over here, depending on what you actually read, and based on which state you are, you can do the appropriate thing of saying, yes, they're equal, or recognizing that they're not equal, and then reject. Okay? So you can encode the fact, what symbol you see by what state you're in, and that's possible because the alphabet is always finite. Okay? In this case, we're working on this particular example, the alphabet is just size 2. Okay? So we'll see that in more detail, but that's something we have to do. And then we're going to cross off corresponding symbols if they are the same. Well, what does cross off mean? Cross off means we're going to overwrite those symbols with a symbol that's not in the input alphabet. Okay, so we have a tape alphabet, which is actually different than the input alphabet. That's the tape alphabet. So let's just have a little example here. Let's say this is 0101, hash 0101, and maybe the tape alphabet has an X in it. Okay, it's a symbol that's not in the input alphabet. So when the 0 is read here, we're going to replace it with an X, which is a good way of crossing it off. And we're going to move into a state here, which is a state remembering a 0, that a 0 was read. And then we're going to be moving right until we see the hash, and then move right until we see something that's not an X, which in this case is just that 0. So we read a 0, and since we're in the state that's remembering that was a 0, then that one is crossed off, and we're good so far. And then that'll move back to the left until we hit the X. And then we move one place right, and we see now, oh, that's a 1. So now we're in a state that's remembering that we're in a 1. Okay? Cross it off, move to the left. Here's the hash. Here's an X. We run until we see something that's not an X. That's a 1. We're in the state that said 1. Oh, that's good. Okay, then we move back. Is everybody getting the idea? And at the end, how do you know whether you're finally finished or not? When all symbols to the left of the hash are X'd out. And how do we determine that? So when we're going back left, okay, we pass the hash, and we make if we see just an X there, then we know that all the symbols on this side have been X'd out. Provided that my rule was always to go, well, the way I said it was, you go all the way till you see an X, and then you move right one step and see whether there's a symbol there other than the hash to X out. So here, if we hit the hash and we move one place left and we see an X, then we go one place back to the right and we see a hash. That's something we can identify in the finite control. Then we know these guys are all crossed off. Okay, when all the symbols to the left are X'd out, check if any symbol on the right of the hash is left. If it's right, it's left. If left, it's right. Okay. Is still there. Okay. And if there is something that's still there, then the two sides weren't equal, and then you reject. If so, reject, else accept. Okay. Now, how do you tell whether whether all the symbols on the right have been X'd out? Okay. So we're Xing out the first one here, and the first one here, and the second one here, and the second one here, and so on. So when you run to the right, you're seeing X's. Okay. And if they haven't all been X'd out, then what happens? You see something that's not an X. Okay. But if they have all been X'd out, then you end up at the right end of the input of what's been written, and you see an empty square. Okay. So we'll have to take account of the ability to know when we're in the right end of the tape. Okay. So this is sort of the the high-level logic, but it's got to be translated into the actual rules for a Turing machine, just the way you translate a high-level algorithm into a program in C or into assembly language. So most people said you've programmed in assembly language. How many people have programmed in machine language? You know the distinction between an assembly language and a machine language. Nobody. Oh, you have. Okay. Yeah. How many people have programmed by sitting on an old I actually did this where I was sitting on the front of some big machine with toggle switches. That was how you were programming. Nobody knows what I'm talking about, so forget it. Anyway, there are more and more primitive ways of programming that are more and more tedious. And programming Turing machines is more tedious than programming assembly language and even machine language. So it's time to start giving you a formal definition of a Turing machine. Formal definition. First of all, we have states. That's the usual thing. And we have a tape alphabet. Okay. And the tape alphabet is actually, oh, I guess I should have, this should have come earlier. This is the input alphabet. So the input is written over some alphabet, and the tape alphabet is not necessarily the same, but it, of course, has to contain the input alphabet because the input is on the tape. Okay? So the tape alphabet can be richer. It can have symbols that are not in the input alphabet, and we've seen that. Okay? We've seen that here, that we were going to X out some of the characters. So we need a symbol X, which is not part of the input. And we need to be able to write a space, or an empty space. That's part of the, no, that's not the right way to say it. Yeah. The empty space is part of the tape alphabet. That's not part of the input alphabet. Okay, so the strings that you write as input don't contain empty spaces. All right. Then the transitions. Well, again, it's going to be a function, delta, the transition, is going to be a function of the states and what you're seeing on the tape. And what you're seeing on the tape might be from the input, but it also might be from what you've written onto the tape. So this has got to be, well, the tape alphabet. And then it's a function from that to what? Well, I've mentioned before what a Turing machine can do. It can move into a state. I mean, it can change its state. So definitely we have to put Q there. Okay, it can change its state. It can also write on the tape, right where the read head is. So that means this next component has got to be what? A what? From the tape, yes, the tape alphabet. Right, good. So it decides what it's going to write, and it's writing from the tape alphabet. Question?
Is it missing the input alphabet?
It's what?
The input alphabet?
You think this should be the input?
On the left side.
No. The left side, this needs to be the tape alphabet, because the Turing machine can move back, and we saw it over here, to read again something that it's written. Okay, so if we just had this as the input alphabet, then we wouldn't have the ability to reread a cell on the tape and be reading something that was written there in the tape alphabet, but not in the input alphabet. Okay, does that make sense?
I mean, like, shouldn't you also include the input alphabet?
Well, the input alphabet is contained there, because the tape alphabet always contains the input alphabet. Right. Okay. So definitely the Turing machine decides what state to go into, what to write, but then I also said it decides whether to move left or right. Okay? So left or right, we use L and R to indicate left or right. And that's what, this is the form of every transition rule. Okay? Now there's one thing that's sort of implicit in this, that we made a big distinction. We were talking about finite state machines. There were two flavors of finite state machines. What were they? Yeah, deterministic or non-deterministic. All right? So I haven't used those words in describing a Turing machine, but if you look at this, which word should you use?
Probably non-deterministic, because we have to be able to use the empty space.
Actually, that's right. That's not right, but it's close. I mean, what you're saying makes sense, but it's not right. This is sort of a hybrid, yes. The empty space kind of reminds you of an epsilon, but it isn't really. It's just another character in the tape alphabet. Tape alphabet. So, no, that's not the critical thing that I was thinking of. Anybody else? Well, this is deterministic because this is from a particular state and a particular symbol on the tape. You're making one possible decision or one possible action here. That's a particular state that you're moving to, a particular symbol that you're writing, and then this is going to be a particular left or right. Okay? So the transition rules are deterministic. Later we will get to non-deterministic Turing machines, but right now the definition of a Turing machine is that it's deterministic. And I think the convention in the book is if they just say Turing machine, then they mean deterministic. Otherwise they'll call it non-deterministic Turing machine. And then later we'll see it doesn't matter because they're equivalent. But anyway, right now we want to make that distinction and point that out. Okay, so then what's left? We have Q0 is the start state. And we have Q accept is a state in Q. That's the accept state. And I also mentioned that in the computation of a Turing machine, as soon as it gets into the accept state, it accepts. It isn't required, as in a finite state machine, that we've exhausted the input. Although for particular languages, that will often be required in order for the Turing machine to properly accept or reject a string in that language. Okay, so, but we allow that that possibility that we haven't seen the whole input. I mean, maybe we're thinking of the language that of all strings that contain at least one 1. Okay, so as soon as you see a 1, you accept. You don't have to see the rest of it. But there are many other languages where you have to look at everything. But formally, a Turing machine accepts as soon as it gets into an accept state. And similarly, it has a reject state. Okay, as soon as it goes into the reject state, it rejects. So this is unlike the case of a finite state machine where it had accept states, but anything else that wasn't an accept state was automatically a reject state. Here, we just have a specified accept and a specified reject, and the other states are not are not either. And then of course we also have this formal requirement that the accept state and the reject state are not the same state. Okay, so those are different states. All right, so this is what it means to describe or define a particular Turing machine. And you should be able, with enough patience and playing around, you should be able to take this high-level logic and implement it in terms of these kind of transition rules, specifying what the states are, what the input alphabet, what the tape alphabet is, and so on, and the transition rules, so that when the Turing machine starts in the start state and it has an input on the input tape, and then it follows the transition rules that are specified, it ends up either as an accept or a reject, and it ends up in the accept if and only if what was written on the input tape really came from this language B, and it rejects, well, this is the equivalent, it rejects if and only if this is not from B. The input is not from B. Okay? So we'll see some examples of that. We're going to do some Turing machine programming. Not this example, though this one, it might be in the book, and if it's not in the book, then maybe you can do it on your homework, your next homework. Okay, so this is a Turing machine, and Turing machines do computation. So we want to talk about computation. Of a Turing machine. Well, I said a minute ago that you start in the start state, of course, and we know where the read head is at that moment. The read head is on the left end of the input, and it's therefore we have a state that we're in, we have what's being read on the tape, and therefore there's a transition rule, or if you've programmed it appropriately, there's a transition rule which says what state you go into next, what you write on the tape, if you write anything, overwriting where the symbol is that the read head is looking at, and then whether you go left or right. Okay, and then you just keep doing that, following the appropriate rule, until you're in a accept state or a reject state. Okay, so as we're progressing, we represent the status of the machine as in a configuration. So represent the status. I don't want to say state of the machine because how do you spell status? Status. It's ES? No, that's states. EUS. Good. Thank you. No, that doesn't look right. How do you spell status? Oh, okay. There we go. Just like it's spelled. Okay. All right. English is terrible spelling in English. It just makes no sense to me at all. I've never figured it out. Okay. So we want to represent the status of the Turing machine, of the computation of the Turing machine at a given moment, or given step. And it's done this way. We know that there's something on the tape. Okay, so here's the tape, and there are various things that are written on the tape. And we know that the read head is somewhere looking at some symbol. Okay, and so we're going to represent this, and this is really and we're in some particular state. Okay, so we're going to represent all that by writing down this portion of the tape, followed by the state we're in, followed by the rest of the tape, and what's on the rest of the tape. And so that tells you the whole tape, where you are, where the read head is, and what state the machine is in. So a specific one might look like this: 1011 Q7 0111. Okay? So this represents the status of the machine, M, where M is in state Q7, okay, because that's written there. The read head is right there. It's the symbol just to the right of where you've written the state. And the tape, what the tape has on it is 1011011111, and then an empty space. Okay, so we can write down the status or the configuration of the machine, and at each step, and therefore follow along what the computation was. Okay, so this is just a convention so that you can understand what's in the book. Okay. And then in the single step of the computation, the configuration changes. Okay, the configuration. If this is the configuration at one given moment of time, all right, then the next configuration. Can you say something about what it's going to look like? I mean, how radically different will the next configuration be from this one? Can these symbols change and these symbols change? You say yes?
I think one can change, right?
Well, yeah, this is the only symbol that can change, okay? Because in a single step, we're going from what state we're in and what symbol we're reading to a state, which may be the same or may be different. And then we write something, but we write it right where the read head is looking. So this is the only symbol that might change, okay? And this might change, so these two might be different. And then where is the read head? Well, it could be here. That's possible if we do a right move, or it could be here if we do a left move, okay? So we're going to be changing the configuration in a fairly small part of the whole configuration. All right. Okay, then the book also discusses what happens to the configuration when you're on the extreme left and when you're on the extreme right, and it's fairly intuitive. Okay, so if U is the part of the tape before the last symbol, which is an A, and you're in QI. So this is the situation where the read head is on the extreme right of the tape, right? And this is equivalent to UA, QI, and then a symbol that represents the space, okay? So the change in configuration isn't really that different because you're reading this space. The read head is right there and can choose to write there, putting something there or not. And then the tape can go right or left from here. So we can deal with this conceptually in the same way we dealt with the others, just by thinking of this as an actual symbol, which it is, in the tape alphabet. Okay, so that's really not so critical. All right, the start configurations. Well, that's obviously where we're in Q0. That's the start state, and then the first symbol on the tape, and then the rest of the symbols. So we're there, and then a rejecting or accepting configuration. That's any configuration where we're in the reject state or accept state. So a computation of the Turing machine is really a succession of configurations where each one corresponds to a transition rule, where each change corresponds to a transition rule. So a computation is a series of configurations starting in the start configuration and ending in an accept or reject configuration. And each successive configuration or each successive configuration is obtained from the prior one by use of an appropriate or the appropriate transition rule. Boy, this is tedious. Okay, this just says what you think it should say. I mean, we start in the start configuration, and then the computation of a Turing machine means it's moving through successive configurations, or we represent its computation by successive configurations. But whenever you look at two successive configurations, the second one has got to be related to the first one by the application of an appropriate transition rule. Okay, and then ultimately we end up, if the computation terminates, we end up in a reject state or an accept state. Now I just said something that never came up when we were talking about finite state machines, and I haven't said yet. Did anybody hear it? A sleight of mind. I said if it terminates. Okay, so finite state machine always terminated because you read one character at each step, and the input was not infinite. It was some bounded length. Okay, but Turing machine computations don't necessarily have to terminate. We terminate if you end up in a reject state or an accept state, but you could certainly have Turing machines that is specified by exactly what we talked about over there and particular input where the Turing machine just keeps going. I mean, you should be able to design one like that without too much thought at this point. Okay, so we need some language to talk about that possibility to distinguish those machines those computations that terminate and those computations that don't. Okay. So, yeah.
Going back, could you explain what U, A, Q, I?
Well, okay, so this U really, this is a string. And this is a single character. Yeah, I didn't really make that explicit. We've used something like that before. Well, maybe we haven't. In my other class that I'm teaching, we use this a lot, where letters from the lower end of the alphabet refer to individual characters, and letters from the upper end of the alphabet refer to whole strings. Okay, so this is a string, and then this was a single character, and because that's what the read head is looking at, or anyway might move past, then we've pulled that out as an individual character. Okay, yeah, and here the same thing. We've got a individual character, and this is where the read head is, and then we have some unspecified string.
So is that like the last state, like U, A, Q, I, or no?
No, this is what it looks like if the read head is all the way at the right end of what's written on the tape. Not necessarily the input, because we may be in a place where the machine has changed the input, extended it, deleted some of it, whatever. But if it's at the right end, then that's equivalent to this kind of configuration. And so this looks more normal in the sense that there's something here to the right of where the state is, and that's all I was pointing out. Okay, yeah, thanks. All right, let's take this out. Okay, so the collection of strings that the Turing machine M accepts, okay, is called the language recognized by M. Okay? Well, we used this word before, recognized. So we have a Turing machine, and given various input strings, it does its computation and does one of three things on each possible string it's given. It runs ultimately to an accept state, in which case that string is accepted, or on that string it runs to a reject state, in which case that string is rejected, or what's the third thing? It spins its wheels and doesn't get to either of those states ever. It just goes forever, okay? But the collection of strings that M accepts, that forms a language. It's a set of strings. Language we defined early on is just a set of strings. That's a set of strings that's recognized by M. Even if M has this property that on some input it just goes forever. That's still defined. Okay. Now the book Computations that don't terminate are said to loop. Okay. I don't like that term. Maybe I'm... Anyway, I wouldn't have used the word loop here because we've seen computations that can go around a loop, as in the finite state machine, but that's okay. There's nothing wrong with that. That's because in the finite state machine, we're making progress through the string, okay? And even though the computation is going back to the same state it was in previously, we're still making progress towards ultimately terminating because we're moving through the string, okay? So loops are not necessarily a bad thing. And in fact, they're necessary in order to have interesting computations. Otherwise, on any finite state machine, the amount of computation you could do is just bounded by the number of states you have. So you could never accept, you could never recognize an infinite language, but we know that we do. At any rate, they say it loops, but I would say it's computation that doesn't terminate. That's my rant. Okay. A Turing machine that always halts, that is on any input, always terminates. That is, it runs ultimately either to an accept or reject state. This is called a decider. Okay? So that's a special word we use to represent a Turing machine which on its inputs always ends up rejecting or accepting. It never terminates, or it never has this behavior that it doesn't terminate. And then a language that is recognized by a decider is called Turing decidable. A Turing decidable language, or just a decidable language. Okay, this lecture's got too many words. Let's see some pictures. Too many definitions, but these will be your critical definitions as we go through our conversation about Turing machines. Whether the language is merely recognized by some Turing machine, is recognizable by a Turing machine, Turing recognizable, or whether the language is Turing decidable. That is, it can be recognized by a Turing machine that's a decider. That Turing machine will always say reject or accept no matter what input it's given, as opposed to only having Turing machines which will accept when it ought to accept, but when it ought to reject, when it's given input that's not in the language, that machine may say reject, end up in the reject state, or it may just go forever. So that's a major distinction between the two types of Turing machines that are available for particular languages. Which one would you rather have? Which is the good guy and which is the bad guy? If you have a particular language, do you want it to be, would you rather it be Turing decidable or just recognizable by some Turing machine? Decidable. Decidable is definitely a good property, okay? And if you don't have a Turing machine that's a decider for that language, and you have a particular input, and that Turing machine just keeps running, you don't know whether it's running and will eventually reject or even eventually accept, or whether it's in some kind of loop and is never going to terminate. Okay? So that's a critical distinction. I mean, if you have that in a program that you're running, and you're sitting there and you're waiting for it to terminate, and it's taking a lot longer than you expect, you often say, well, is this, if I give it another, maybe you don't ever have this experience, but I do, and some of the things that I do, you say, well, maybe if I give it another hour, maybe if I give it another day. Yeah, I mean, whatever I can tolerate. Maybe it will terminate eventually, or maybe it's just going to go forever, and I better kill it. So these are important distinctions, and the critical distinctions we'll get into. All right, let's program. Okay. So here's the language. A equals 0, 2 to the n, 0 to the 2 to the n, such that n is greater than or equal to 0. First of all, what is this saying? What's the input alphabet here? Just 0, okay? It's a unary alphabet. I don't think we've seen any of those before. And the 2 to the n says it's a repeat of 0 2 to the n times for some n. So the number of zeros is a power of 2. Okay, so this is a unary string or unary strings, well, of lengths. Let me just say unary string. So W is contained in A if and only if W is a unary string of length that is a power of 2. Okay? So, for example, what about the empty string? Is that in this language?
No.
Good. I don't think it is. Yeah, I don't think the empty string is in here because the only possibility would be when n is equal to 0. But 2 to the 0 is equal to 1, right? So that would be a single 0. So it doesn't look like the empty string is in there. A single 1, we just said it was in there because you could take n equals 0. So 2 to the 0 is 1, and that's just 1, 0. What about 0, 0? Yeah, that's in there because n equals 1. How about 3 zeros? That's not a power of 3 is not a power of 2, so that's not in there. And that is in there, and so on. Okay. All right. Is this a regular language? Good exam question. Oh, and speaking of an exam, by the way, I hope everybody remembers that the midterm is not this Thursday, but the Thursday after. So midterm on I think it's the 27th of October. Yeah, that was on the syllabus. So we'll have I'll say more about the midterm as we get closer to it, but it's coming up next week. All right. Is this a regular language? What would you do to... Well, obviously what you do if you want to prove that it is a regular language is you have to come up with a DFA for it, or an NFA, whichever is easiest, or a regular expression, whichever way is convenient for you. But how would you prove that it was not a regular language? Yeah?
You use the function lemma, and you'd have to make t to the n be larger than the number of states in the DFA, because then you would repeat all of the first p characters. If 2 to the n is larger than that, then you know you wouldn't get to the next power of 2 or less.
Yeah, I think that would work. I think you could play that out and make all of that work. Yeah, you could use the pumping lemma to prove that this was not a regular language, and so that sounds like a good homework exercise or a good exam question for the midterm. Okay, but now we have Turing machines. So you might also think about whether you could do this with a PDA. I don't know, but. Now we have Turing machines, we've got a lot more power. So how do we, but still we don't have numbers. Turing machine doesn't have, well, I shouldn't say it doesn't have numbers. It can write things on tapes, and so, on a tape. And so you might be able to think about how a Turing machine can actually deal in numbers. But we're not going to actually need to have numbers. So most of the logic you have to think about in terms of you only have a finite state control in there. What are you going to do to recognize whether something is, the number of zeros is a power of 2 or not? Any idea? Well, let's do a little example, not the Turing machine itself yet, but just a very primitive way of determining whether some list of zeros, if the number of them is a power of 2. So what is this? 1, 2, 3, 4, 5, 6, 7, 8. Power of 2. Okay? So one algorithm, high-level algorithm, that should sound like you could translate it into a Turing machine, the computation of a Turing machine, is to make multiple sweeps here and cross out every other zero that you encounter. Okay? So the first time we sweep left to right, we're going to cross out that one, cross out that one, cross out that one, cross out that one. Okay? And then go back to the beginning And again, we're going to cross out every other 0 we encounter, but now we also are going to be encountering x's. Right? So you encounter an x, you don't do anything about that. Encounter a 0, okay? Then you encounter an x, don't do anything about that. Then you encounter a 0. Well, that's not, if I said we're going to cross out every other 0 we encounter, okay? So is this the every or the other? It's the one we shouldn't cross out, right? We crossed out that one, so we're not going to cross out that one. Okay? That one we cross out. Okay? And then we don't cross out that one. We hit the end, we recognize we're at the end, and we go all the way back here, and we sweep again x, x, x. Here's a 0. Okay? So we cross that out. X, x, x. Here's another 0, but that's the one we don't cross out. Okay? Hit this one, go back, and then go back here and cross it out. So yeah, and then we have all the x's. And if you think about the logic of what I was doing, every sweep is crossing out half of or roughly half of the zeros that are there. Every other one. So if we end up crossing them all out, then that was a power of 2. If we don't, then it wasn't. Somehow I believe that's right, but it doesn't feel right at the moment. We don't think about it. Okay. Okay, so here's how we're going to encode that in the Turing machine. I could write down all the actual transitions, but that's tedious. So again, we're going to have a diagram which shows you what the logic of the Turing machine is. And that diagram has shorthand in it. So let me write it down and then explain it to you. Q1 is the start state. I pointed this out before. The book has an inconsistency, which doesn't really matter as long as you keep your wits about you. In the definition of the start state of a Turing machine, it was Q0. But a lot of times when they're showing actual start states in diagrams, it's Q1. Doesn't matter. Here we have the arrow that goes into it that's okay. This is only a little piece of the Turing machine of the diagram. But let me explain what these are saying. This is saying that if you see an X, if you're no, let me make sure I know what this means. Hold on a second. Okay, yeah. Let me just give another piece up here so I can explain that one too. Q2, 0 goes to okay, so that means that yeah. So if we're in state Q1 and we see a 0, then we're going to write a blank, and we're going to move to the right. Okay, so this is encoding the transition rule and move to Q2. So this is encoding the transition rule that says state Q1, this is what you see, and then this is what you're going to write, and this is where you're going to move on the tape, and this is the state you move into. So all the components of a transition are represented by this piece here. But here we have something that looks a little bit different. That's what I had to check to see exactly what this meant. And this means that if we see a blank, then we're going to move right, and we're not going to write anything. There's nothing that's written. And here if we see an X, we're going to move right, and nothing is written. And we move from state Q1 to the reject state. Now you're not going to see the logic of the whole thing here until I put in much more. But I wanted to write this just to start showing you what this shorthand means. This is what you're what the read head is looking at. This is the state you're in. the state you move to, what's written, and whether you're moving right or whether the read head is moving right or left. Okay. So okay, let's just look at this thing. So here we're seeing X's. That's the symbol we're using for marking off characters or marking out the zeros. We're seeing X's and we're not writing anything. We're just moving right. Okay? So this is a part of the computation that I was talking about earlier, where you're just zipping through whatever X's you see. All right? And then here, you're seeing the right end, right? The right end of the tape because you've hit the blank. Okay, so if you're zipping through the X's, you're seeing X's, and then you finally hit a blank, you're going to go right and accept. Now we have to see the rest of the machine to know that this is the right thing to do. But as I'm writing this out, I want you to think about the basic computation I was showing you earlier, where we're going to make multiple passes, Xing out every other zero, and then finally, if we end up zipping through everything and everything is X'd out, and we hit a blank, then we accept. And this is part of that implementation. Zipping through X's, moving right each time, not writing anything on the tape, and then finally we hit the blank at the end, we go right and we accept. Okay, well what happens if we see a 0? If you see a 0, what this is saying, we want some part of the Turing machine, and this is sort of like a finite state machine at this point. We want to build some states and some transition rules that say X out every other 0 that you see. Okay? So if you think about the initial computation or computation from here, you're saying here's a 0, you're turning it into a blank. That's so we can detect when we're on the left end, by the way. We don't use an X in that case, we just use a blank. And then you go right. Now you're just seeing X's. Now you're seeing an O, and you want to X out every other one. So you X that one out. You go right, and you move into Q3. And now you might see a lot of X's again. So you're zipping through those, not doing anything with them, just in here, and here you see another O, but you don't want to exit out. Here we X'd out an O. So the next O you see, or next 0 you see, you should not X out, and that's what's done here. But then the next one you see, you should X out. 0 goes XR. Okay? So you can see what this is doing. It's every other, this whole piece in here, every other 0 is being X'd out. And in between those, every other 0 might be many X's. That's okay, you just zip through them. You zip through them. But every other 0 that you see is X'd out. So this 0 is red, but you just move right without writing anything. And then here, you change that 0 to an X, and you keep doing that. Okay. What else do we need? Need something up here. Q5. Empty string goes, empty string goes left. Okay, so what's happening here? Here you're Xing out every other 0, and you finally hit the right end of the tape. You see the blank. It's the right end of the tape. And so what should you be doing now? You need to go left, back to the left end of the tape, right? So here's your first move to the left, and then we'll have here 0, you go left, X, you go left. So this is just the part of the control that's going back. It was at the right end. It's zipping all the way back to the left end. How does it know that it got to the left end? How does it know when it gets to the left end? Well, remember here, in the first 0 that you saw, you turn it into a blank. Okay? So when all of this zipping around finally hits a blank, then you know you come back to the first guy. So really this first one, it shouldn't have been X'd out. It should have been made a blank in terms of this logic. The basic logic of well, anyway, that should be made a blank according to this logic and according to the ability to, in order to have the ability to recognize when you're at the left end of the tape. So here we go. We're seeing a blank, and what should where should the tape move now? Where should the read head move now? So when we see a blank at the left end, where does the read head go? It goes right. Okay? So that's that part. And then we have this one. Yep. Empty goes reject. So what's happening here is that we're seeing an odd number of zeros, and an odd number is never a power of 2. A power of 2 is never an odd number, except for 1. That was somewhere here somewhere. And so there, if you hit the right end, you want to reject. Okay, I think I've written it all up, and I think you're going to have to look at this yourself to convince yourself that this really works, and convince yourself of what the high-level logic is that really works. So if you, this is in the book. In this class, I'm trying to stay very close to the book. So, by the way, I meant to pass around your homework too. So see how far that gets. This is on page 144. So take a look at that and try this out with some examples where the number of zeros is a power of 2 and when the number of zeros is not a power of 2. And just convince yourself of how this is working, what these notations mean, and that the logic, the general approach, is working. Okay, what I have next is another example, but we're kind of running out of time. And so I'll do the next one next time. But it'll be an example of how a Turing machine can actually do some arithmetic. So let me just show you, while those pages are going around, what the next language is that we're going to look at. So C is equal to A repeated I times, B repeated J times, C repeating K times, where I times J equals K. And Ij and K are greater than or equal to 1. So we're going to see that the Turing machine can do multiplication. It can check whether basically I times J is equal to K, but it's doing it in a very tedious way, whether the number of A's times the number of B's is equal to the number of C's. But again, multiplication is something, if you try to do that with a finite state machine, I think you'd immediately get stuck and have a good intuitive appreciation for why something like that is very difficult on a finite state machine. And But when we're programming Turing machines, then you'll see that that's possible on a Turing machine. Okay, we've got a couple of minutes left, but this is a natural place to stop. And